Here we demonstrate the computation of the causal attention by using masks. We start from the computed per channel per head attention. Here we have 4 examples, 4 data instances for each of the data instance. There are 8 channels. For each channel, we compute the attention between the 50 locations. To make the visualization a little bit easier, when we print the logs, that will not just flash the screen. We can take the subset of those locations. So remember that this will be the query has now been organized in the way that the instances, 8 channels, so we take all the instances and all the channels. But now let's take maybe instead of the 50, take only the first 5 locations and take all the vectors, subvectors. Okay. In this way, we consider only the attention between the first 5 locations. Oh well. Okay, now it's 5 by 5. The task here, let's just inspect one particular piece of attention matrix. Let's consider the first example. And its first head, and consider its attention. So that is attention. We would use this attention to combine the values. Of course, for the values, we will also take the first 5. So those are the ways that will be used to combine those values. Okay. Therefore, we want to make those parts just 0. Okay. Here is some further processing steps. I think it's better to just introduce here. Instead of directly use those raw attention scores to combine those the value vectors to form the output, we convert this into probability distributions. To do this, we first scale the scores according to the length of the feature vectors, which makes sense if you think that each of the attention weights computed here. Okay, I think the sync between my, okay, let me do this. Each of the attention, oh, it comes out. Okay, as the attention weights computed here, it's the result of a feature vector. This is a Q feature vector times the K feature vector, and that is the element-wise multiplication and take the sum. So we do not want the arbitrary choice of how large a feature vector we want to use to affect significantly on how we would compute the attention. We want the feature vectors is to automatically learn which reflect the relevant information, but on how to emphasize at each relevant information, we don't want the size of the feature vector affect that. We want the relationship themselves to manifest in the weights. So we scale the weights using the size of using the inverted size length of the feature vectors. So what we are doing here, if the length is k here, well, the k, I think I abused the symbol, maybe let it to be p here. We will divide the scores choosing square root of p. So here is where is my mouse? Okay, this is what we do. I do it in 2 steps. Scored. Do I have the math library? Anyway, I'm taking SQR square root of the size of the feature vector, which we can just simply use uk dot size the not this one, shape. Okay, the last one. Now let's compare. See, this is scaled. So after scaling, we will compute, we will scale it again using softmax to convert each row of this matrix into a probability distribution, which means we will convert all those scores in between 0 and 1 and let them sum together to be 1. The implementation is in this way. I think I have the functional, yes, softmax, and we do self, and the dimension should be the last one. So now when we have a look at this, this will sum to 1. Do I need to check? Maybe. And the dimension, let's be -1. Okay, what the heck? Oh, softmax typo. Dimension isn't defined. Okay. Okay. See, each row of this matrix will get a dimension of 1. Now, it is an extra step to apply the mask. We can just put zeros in this part, okay, or alternatively, we can set up minus infinity to this part, because the minus infinity will becomes zeros after the softmax. So we can do it either way. But before we do that, we need to first set up a mask. Okay. To set up the mask, we need to be able to form a triangular matrix which has the desired entries filled this way. Okay, we can this will include the diagonal elements. We can freely choose to mask this part or mask that part. It doesn't matter. So PyTorch provides us a functionality of triangular, and we this will take the lower part of the triangular matrix and call it once. Okay. This should be 50 by 50, but here, just for example, we take 5 by 5. Let's see what we have. Yes. So basically, what we need to do, we can just multiply this element-wise to the computed scores. Oh, but sorry, we can't, because in this way, we will nullify some of the computed weights, so we no longer have the sum to 1 property. We need to fill the negative infinity to those pre-transform scores. Okay, we can just do that. Consider if this is 0. Okay, now we have flipped the mask. Let us to take the temp. Okay, temp s temp s dot mask. I always use Google to, trust me, I just Googled the signature of the function and the, how to use it. So if you are like me, don't worry, everybody Google those functions while using them. Okay, so let it to be 0, and I will fill minus infinity here. Float minus infinity. Let us see what we will have here. Okay, nice. Now we have a diagonal matrix, and with only the lower part of the matrix have non-zero values, and each row of that matrix sum to 1. So this is a way how to do the causal attention. In the next step, I won't show the details of each combination, but we will put things together, and in the next video, I will go through the complete code of a causal attention block.